Look at this problem 1650, lowest common ancestor of a binary tree 3. Given two nodes of a binary tree P and Q, return the lowest common ancestor. Each node is going to have a reference to its parent node. Lowest common ancestor is the lowest node that has both P and Q as descendants, where a node can be a descendant of itself. So we're given this 5 and 1. So 5 and 1, the ancestor, their common ancestor that's the lowest would be the 3 here. And then here, this tree, 5 and 4. So 5 would be the lowest common ancestor. Okay, and if you have just 1, 2, then it's just the number 1. Okay. So this is P and Q. So you're given just P and Q. So usually the previous lowest common ancestor problems would come with like the root and then the P and Q, and then you would take the root, kind of iterate down until like you hit the P and Q, and then you basically find like the lowest root that has both P and Q, where root would be like the root of a subtree. But in this case, you're not given a root, you're only given P and Q, so then you have to iterate using its parents. So if you look at this example here, so if we got 3, then 5, then 1, then 6, 2, 0, and then 8, and then 7, 4 here. So this is just a binary tree, not a binary search tree. So then if you start with 5 and 1, so if you just go up their parent, if you check like 5.1 parent, so it's basically the 3, and then the 1 dot parent is also the 3. So then in this case, 5 dot parent equals to 1 dot parent. So then we just return, so it would be a 3. It would be they both have 3, so then you just return either's parent. So you could just return, like, let's say 5 dot parent. And then let's look at this second example. 3, 5, 1, 6, 2. Oh, it's the same tree, but 5 and a 4. Okay, so basically here you will see that 4 is clearly lower than a 5. So you go to 4 dot parent, then the 2. 2 still below the 5, so then the 2 dot parent would be the 5, and then now they will hit. So in this case, you would do 4. You'll say 4. Then you look at 4 dot parent, which is the 2. Then you look at the 2 dot parent equals to 5. So then basically here, so Q is the 4. So 4 dot parent equals 2. So then you basically say here like Q equals Q dot parent. And then here, Q dot parent, this is basically the same as Q dot parent equals P. So if you take P equals 4 dot parent, which is 2, the 2 dot parent is the 5, which is the same as P. So then that's another case. In this case here, we just return P. So then if you had the opposite, where if you have P dot parent equals Q, then you return Q. So we basically had the conditions for when they equal. Now we have to figure out, how do we iterate the parent? Like, how do we know we check Q dot parent but not P dot parent? So in this case, P was 5, Q was 4. So basically we iterate 4. We look at 4's parent but not 5 because 4 is below 5. So here we basically know that Q is lower in tree than P. So that implies look only at q dot parent not p dot parent. So then how do we know if it's lower? So then we basically need some method to compute like we can call it like the depth or like the height of a node. So to do that, what we could do is we could look at this for, keep looking at its parent until it reaches the root and it no longer has a parent. So if we do something like height of node, we can start with h equals like 0, and then while node dot parent, then you would increment h, and then node equals node dot parent. So here you start at 4, it has a parent, so you go to 2 and then you increment h. 2 has a parent 5, 5 has a parent 3, 3 no longer has parents, and then you increment h basically 1, 2, 3 times. So this would have height 3, and then the 5 would have just height 1. So then so in this case, so we could just say q is lower than p, which is the same as height of q is greater than height of p. Then we would look at q dot parent, not p dot parent. But what if they're in separate trees? Like let's say we got the same tree, but then we're looking at, let's say, the 5 here and the 8 here. So let's say p equals 5q equals 8. So then height of p would be, so you just go up once and then you hit the root, so it'd be 1. Height of q would be 2 because you go from the 8, 1, and then the 3. So then, but in this case, actually this is not a great example because here, okay, so first you know q has the higher height, so then now you increment, so then you basically look at q dot parent, not p dot parent. So you look at 8's parent, which is 1. And then now you check if they both have the same parent, which they do, which is 3. But let's see, that might not have been the best example. Okay, let's do 7 and 0 instead. So 7 is going to have 1, 2, 3. And then q is going to have, so 1, 2. So 2. So then looking at this, you say height greater than q, or height of p greater than q. So only look at p dot parent, not q dot parent. So then that implies now that p equals p dot parent. P's parent is the 2. So now, okay, so now p is 2. Q equals 0. So they're at the same height now, but their parents are not the same. So then in that case, here, equals height of q, but p dot parent doesn't equals q dot parent. So in that case, here the 2 and the 0, so you increment both of you will look at both of their parents. So implies p equals p dot parent and q equals q dot parent. So it looks like now we have all the conditions. So basically, so we compute the height with this. Q lower than tree implies, so Okay, so Q is lower entry than P, then height height Q is greater than height of P. Then look only at Q dot parent, not P dot parent. So then basically you have Q equals Q dot parent. And then similarly, if you swap the P and a Q. So then let's look at if they're the same. So if they're the same, but their parents are not equal, then you increment both of them. And then here, so then here, if their parents are the same, then you just return the parent of one of them. So if their parents are the same, then you return P dot parent or Q dot parent, doesn't matter. And then, so basically the conditions are one has a height greater than the other, then you increment the lower one's parent. If they're the same, but their parents are not the same, then you increment both of them so you go up to their parents. If they're the same height and their parents are the same, then you just return the parent. So looks like we have our algorithm. Let's code this out. Okay. So first we're going to have, let's call this like HQ, HP equals self dot height of Q, self dot height of P, and height would be self of node. So it's basically this. While node dot parent H plus equals to 1, node equals node dot parent, and then turn H. Okay, and then now we have these conditions here. If HQ greater than HP, Q equals Q dot parent. You should have a while. And then you would decrease the height by 1. And then the opposite way as well, where P and Q are swapped. Then now we know they have to be equal. So if P dot parent doesn't equal Q dot parent, so then this would be a while loop. You would keep doing it until their parents are the same. And then here, they basically had the same height and the same parent, so then you just return one of their parents. And it looks like that should be it. So let's walk through, let's double check the code. Height of Q and P, node H0. So let's get this 5 here. So node up, increase height by 1. Node equals node parent 3. Node is at the 3 now, it doesn't have a parent, so you just return the 1. This will also be 1. So they're both 1 here. None of these hit. This doesn't hit because they have the same parent, which is 3. So you just return 3. Let's look at this here, 5 and 4. So this is gonna have height 1. This is gonna have 1, 2, 3. So then HP would be 3. HQ would be 1. Yeah, Q is the 4. Okay, so HQ would be 1. HQ is greater than HP, so then Q equals that Q dot parent, and 4 equals to 2. Decrease the height by 1. Then 2. So now you're at the 5 and a 2. So, okay, so this is wrong. while HP and Q dot parent doesn't equal to P. And then similarly here, and no, here. And P dot parent doesn't equal to Q. And then now, so in this case, you're at the 2 and the 5. So the 2's parent is the 5. So then basically, Q dot parent equals P. So in that case, you can have if Q parent equals P, return P. If P dot parent equals Q, return Q. So we could have that to save an extra step, or we could just get rid of this, in which case the height of Q is less than, no, this is Q. Yeah, height of Q is greater than height of P, so then you would set Q equals Q dot parent, and now they're both at the 5, in which case you can skip this. And then comment out this. So now they're the same height. So now they're both at 5. So their parents. So I guess what we can have here then is if Q equals P, return Q. And then otherwise, they're at the same height, but they're not equal to each other. They just increment their parents. Yeah, so in this case, like 6 and 2. So this is wrong, actually, because here, let's say you have 6 and 2. They're not equal to each other, but they're at the same height. So then here, while parent doesn't equal each other, so in this case, their parents don't equal to each other, but no, their parents do equal to each other. So you're not hitting this. So we could also do then is if Q dot parent equals P dot parent, return Q dot parent. There. So then now you have two cases where their heights are the same. If they're actually the same node, you just return that node. If their parents are the same, return the parent. Let's say you have the 6 and the 0 here. They're at the same height, but their parents aren't the same. So then you increment their parents, and you have 5 and 1. And then now they have the same parent, so it'd be the 3. Okay. So it looks like this should work then. And it passes all test cases. So that's it. Thanks so much for watching this video.